This is section 6.3, and today we're going to start talking about vectors. And the notes are more filled in for you than normal. Vectors are usually the section that students have the most trouble with, I think because it's mainly vocabulary. The mathematics is not difficult at all, but the vocabulary will kill you if you're not making some flashcards. So if I could suggest that, that would be great. And it's not just what the things mean, but like how to find them or what formula to do. So let's start and then I'll give you kind of an example. So some quantities like area, time, temperature, they can be represented by one number. Other quantities like force and velocity need both. They need two different things. They need both a direction and a magnitude. Here's one word for you already. If you don't know that magnitude means length, you wouldn't know to do the simple distance formula that you've been doing for years. So maybe magnitude on one side of the card, length, distance formula on the other side. So you're just practicing what is the word, what does it mean, and then what formula am I going to use. So to represent those quantities, you can use a directed line segment, which has an initial point and a terminal point, somewhere to start and somewhere to end, sometimes called a vector. So I'm going to draw one over here. We're going to start at P, we're going to end at Q. So this is my initial point, this is my terminal point. The vector PQ, when I go to write it, I would say PQ with, and it's going to look like an arrow, but you only do the top half of the arrow. That's how you designate a vector. Another way to do it, if you're on a picture that maybe doesn't necessarily have the start and beginning letters, this might just be vector U, maybe in some other problem or book, and we'll do some like that. So as long as they're bolded, like this, or since you don't really have a bold pen when you're taking notes, you would just do a letter and then a vector above it. So that's how you do notation for vectors. The vector's length, or again, its magnitude, looks like this. We denote it like that. It's kind of like a double absolute value. So when you see that symbol, if I say find that, you have to know that that means magnitude of v. And then you would do something as simple as the distance formula, which you've been doing for a long time, just in case you forgot. Whoops, equals and that is the distance formula. So the only word you've learned so far really is magnitude, besides vector. That's what we're talking about. So magnitude means that you're finding the length of something, the distance. And so two vectors are equivalent if and only if they have the same direction and magnitude. If that's what makes up a vector, then they have to have the same stuff in order to be equivalent. So as long as the two vectors are going in the same direction and they have the same length, then they are the same vector. So for an example, let's have v be the vector from 0, 0 to 4, 5, and u be the vector from 2, 3, 6, 8. We're going to show that they are the same. What needs to happen for the vectors to be equal? They have to have the same direction and the same magnitude. So just to give a picture of it, the first one is going from 0, 0 to 4, 5. 1, 2, 3, right there. And that is the vector u. Nope, sorry, that's v. And then the vector u is going from 2, 3, right there, to 6, 8. Right up there. And we're going to show that they are the same vector, that they are in fact equal to each other. So first I need to show that their distances are the same. So they need same magnitude. So I'm going to do the magnitude of u and I'm going to do the magnitude of v, and we're going to find out that they are the same. Oops, missed that. So the magnitude of u, 6 minus 2, and 8 minus 3. So 4 squared and 5 squared. If I put those together, I'm going to get 41. Doing the vector v is going to go from 4 minus 0 and 5 minus 0. So it actually ends up being the same thing, which is good. That's half of our proof of how they're the same vector. I also need to prove that they're the same direction, and direction means slope. So I'm just going to do slope of each one and show that they are the same. So the slope of vector u is y minus y, so 8 minus 3 and 6 minus 2. The slope of vector v is going to be 5 minus 0 and 4 minus 0. So they are the same vector, they have the same slope and the same magnitude, and that's how you show they're the same. Component form of a vector. Here's another vocab word, what component form means. It's actually pretty easy to figure out. All you do is subtract, but if you don't know what component form means, it's very difficult. So a vector is in standard position if its initial point is at the origin, so like v. V is considered to be in standard position. It doesn't have to go in the first quadrant, it could go anywhere, but just as long as its starting point, its initial point starts at the origin, it's considered to be in standard position. If a vector is from these 2 points, from this point to this point, then its component form is, and you subtract terminal minus initial. Terminal minus initial. You're trying to determine what the vector is doing. Which direction did it go? So standard position again just means that the vector starts at the origin, could go in any direction, could be any length. So the component form of vector u from above, this one right here, which is not in standard position, but doesn't have to be. I just want to find its component form. And component form says I just subtract terminal minus initial. Make sure that you look where the 2 is, because that means that's terminal. So 6 minus 2 and 8 minus 3, 5. And when we're talking about vectors, you switch from parentheses, which are points. These are ordered pairs. These are points, to kind of a bent parenthesis that is denoting component form. So now you're talking about the vector. This is not an ordered pair. This is what the vector is doing. What the vector does. It goes to the right 4, it goes up 5. The interesting thing about vectors is they don't have location. So a vector could be anywhere, and as long as it goes up, over 4, 1, 2, 3, 4, and up 5, 1, 2, 3, 4, 5, it is the same vector as this one, 1, 2, 3, 4, 1, 2, 3, 4, 5. Vectors do not have location, they just have magnitude, length, and direction, which is slope or that angle. So this vector u, which is 4, 5, is the same as this one, is the same as this one. As long as you go over 4 and up 5, you are all the same vector. The magnitude or length of a vector, once you already have it in component form, you can kind of shorten up the distance formula a little bit because you've got it down to just these 2 values. So you know how far over and how far up. What you're essentially doing is Pythagorean's theorem. You know the over and the up, and you're about to find the hypotenuse. So that's found by taking each one of your sides and squaring them. And then just rooting the answer for whatever you get, which is just a shortened version of the distance formula, like I said. You're like doing Pythagorean's theorem. You went over some, you went up some, and now you're going to find the hypotenuse. Or maybe you went left and then you went down, but you're still finding the hypotenuse. So it's just a shortened version kind of Pythagoras and even of the distance formula. So the next example says find the component form and the magnitude of the vector from here to here. Initial, terminal. So the component form is x minus x, 5 minus 2, and y minus y, 7 minus negative 4. The magnitude of this vector, and they didn't give me a letter, so I'm just going to throw a u in there, is just these 2 numbers rooted. So I should have said the square of those 2 numbers rooted. I could back up all the way over here and do the distance formula, but I would do 5 minus 2, which is 3, and I would do 7 minus 4, which is 11. So once you find component form, you're kind of halfway done with your distance formula as well. So doing this, simplifying this distance formula on the test, square root of 130 is perfect. If you give me the decimal, that's okay. It's not wrong either way. Vector operations. So we've got some vectors and we want to start talking about what we can do with them. So here I've got 2 different vectors, u and v, and then k is a real number named a scalar. This is just something we're going to multiply by. We used to call it a coefficient. But for fun in vectors, we call it a scalar. So when you have two vectors and you want to add them together, you just add your x's together, so u and v. And then you add your y's together, u2, v2. So it's really not that difficult. You add vectors together, you add the x's, you add the y's, there's your vector. As a picture, what it would look like is, let's say this was my u vector, and let's say this was v. If I want to add them together, what I do is I pick this vector up and I put it at the end of this one like I'm making a train. So I'm going to pick up v and I'm going to put it right at the end of u. Same magnitude, same length, same direction, and it's going to look about like that. I'm just eyeballing here. This is u plus v. The answer, the thing you want to give me on the test, goes from beginning to end. This is called the resultant vector. This is the answer. And it doesn't matter if you did u and then v, or if you took u instead and moved it over here. If you took u, that one right there, and moved it right here, you would still get the same r. Same length, same magnitude, same dotted line. This is the resultant. This is u plus v. Resultant vector. Scalar multiplication is what if I took a number times a vector, and it does exactly what you think it would. If I put a 5 out in front of my vector, it just means I distribute a 5, they both get a 5. So the k would times the u1 and k would times u2. So whatever you had for x and y, if you threw a number out front, you just multiply it through. What that would look like is, let's pretend that this is our u vector, has a magnitude of 2 dotted lines and just a little bit of a slant to it, a little bit of direction. If I decided to do half of a u, it's just going to be half as long but same direction. If I decided to do 2 u's, logically that would be twice as long. So it's going to be 4 dotted lines. Same direction, I haven't changed my angle at all, just longer. If I do a negative u, means the exact same vector but pointing the other way. So 2 dotted lines, same slope, arrow is going the other way. So if I wanted to do, let's say, negative 3/2 u, so I need 1.5 dotted lines, same direction, same angle, just 1.5 lines long. We're going to do a little vector addition and subtraction with these. So the first one says let v be negative 2, 5 and w be 3, 4. Those are the two vectors. They're in component form. I want to find the following. What would 2v look like? So this would be 2 times negative 2, 5. And it literally just becomes negative 4, 10. Not difficult on the math at all. What I want to do is show you what it looks like as a picture. So if I were to plot this, negative 2, 5 is going in the left quadrant. 1, 2, 1, 2, 3, 4, 5. There's my first one. It went left 2, up 5. From that point, if I want to do a second v, I need to start right here. So pretend like that's your new origin. I need to go left 2 and up 5. The resultant vector, the answer, it's kind of tricky to see in this one because it's right on top of it, is from start all the way to finish. And that vector would be left 4, up 10, which is exactly what we got. On the next one, you'll be able to see the picture a little better. So w minus v, I'm going to take 3, 4, and I'm going to subtract v, negative 2, 5. The algebra really is as easy as it looks. So 3 minus a negative 2 would be 5, and 4 minus 5 would be negative 1. So this vector is going to the right 5, down 1. Just want to give you a picture so you can see what it looks like. The first vector was 3, 4. So right there. The second vector has to leave at the end of the other one. You don't go back to the origin. You have to keep your train going. And this one's supposed to go left 2, up 5. Sorry, we're subtracting it, so it's got to go to the right 2. We're doing the opposite, down 5. I was just reading this part right here. We're doing the opposite of it. Negative makes it opposite. If you were to distribute that in there, you would actually end up with 3, 4. And then you'd have your negative I'm sorry, positive 2, negative 5. So you're going to the right 2, 1, 2, and then down 5. 1, 2, 3, 4, 5. So your resultant, your answer, is this one right here, which went over 5, down 1. So we're matching both in the algebra and in the picture. Next one is v plus 2w's. So a v is negative 2, 5, and a w is 3, 4. Mathematically, first you have to distribute the 2. So we have negative 2, 5, and 6, 8. And then when I get done adding this, negative 2 plus 6 is 4. 5 plus 8 is 13. So that's the vector we're going to graph, but we're going to do it this way. So first I'm going to graph the v vector, which is going left 2, 1, 2, 3, 4, 5. So the first vector is right about there. That's v. W has to go right off the end of this one. So W is going to go 3, 4. 1, 2, 3. 1, 2, 3, 4. And then it's going to do it again. 1, 2, 3. 1, 2, 3, 4. My hand shook a little bit there. It's not very straight. Your resultant vector is this one. This is the answer you give on the test. This is like telling me 1 plus 2 is, and then you have to actually tell me it's 3. So don't forget to draw the dotted line at the end, draw your resultant at the end, which should match this. So does it look like we went over 4 and up 13? It sure does. So that's how you add that one. Next up, we just have a negative v. That just means I'm going to take v and flip it, make it go the other way. I'm going to change its signs. So I'm going to go to the right 2 and down 5. And that, oops, missed my dot. And that is what a negative v looks like. Normally v would have been negative 2, 1, 2, and then up 5. So as long as we are going in the opposite direction, same magnitude, we did a negative vector. Lots of vocab, like I said. The hardest part is you learning all the vocab, knowing what a scalar is, knowing magnitude, component form. The algebra, the math behind it really isn't that difficult. Distance formula, a little bit of adding and distributing. The math is not tricky, it's just the vocab that's going to hurt.